Anyway, so today's topic is going to be the Cartesian plane, which I think is probably one of the relatively easier today, as a lot of these concepts are building off of things you probably have already learned to a certain extent in school. And by the Cartesian plane, I'm referring to just the set of coordinate axes of the x and y, and these numbers are going like from like 0 through infinity, 0 to negative infinity, and so on like this. And it's just like basically just a grid, and I'm sure you've all seen it before. So yes, and some important things that I want you guys to, what I consider to be the most important parts of problems that involve the plane are the distance formula between 2 points, which is just derived from the Pythagorean theorem, where if you have 2 points, x2, like x2, y2, and let's say it's x1, y1, then you just subtract the x coordinates, and you subtract the y coordinates, and then use Pythagorean theorem to get their distances. And since the square of the positive and negative values of these are the same, it doesn't really matter which order you subtract them in. Okay, and for lines, they're in the form of y equals to mx plus b, or at least this is the slope-intercept form of it. You might see it in other kind of forms, but you can always reduce it into just y in terms of x. And basically m is the slope of the line and b is the y-intercept, and the intersection of any two lines is going to be the solution of the system of equations of the two lines. So like if you have the lines like, sure, like 2y plus 3x equals to 7, and let's say y equals to 2x, their intersection is just going to be the point xy that satisfies both equations. In this case, is going to be 2, 1. Anyway, and regarding slopes, this is where we can apply coordinate geometry, where we have that if the slopes of two lines, like the m here, they're equal, then the slopes can be parallel, which means they don't intersect. And if the slopes are negative reciprocals of each other, like 2 and negative 1/2, or 4/5 and negative 5/4, then the lines are going to be perpendicular. And if we have two lines that are opposite slopes, such as like 2 and negative 2, then the lines are just going to be reflections of each other over horizontal or vertical lines. And I'll just demonstrate that. Where if we take the lines y equals 2x and negative 2x, 2x was that and negative 2x is like that, it should intersect at the origin. That you can see that if we reflected y equals 2x over the y-axis or the x-axis, we would get y equals to negative 2x. So basically the slopes would just be a negation if we reflect it over a horizontal vertical line, which have slopes of 0 and undefined. I don't think you guys have any problems with that, right? So moving on. Equations of conics, which are basically just, you can just think of them as curves, but like they're formally defined as like graphs you can get if you intersect a plane with a cone. It's named conic. It's actually going to be a cone. It's not really relevant. But either way, the equation of a circle is going to be x minus a squared plus y minus b squared equals to r squared, which is a circle with radius r centered at AB. This is the most commonly seen one, and it's really important to remember it, as you'll often see equations that are x squared plus some number times x plus y squared plus some number times y equals to another number in problems like this. And then what you have to do is you have to complete the square for both x squared and y squared to get a circle, which you can graph. And these are just two different ways to write an equation of a parabola, which just looks something like that, or like that. Again, these are pretty standard in school, so I'm not really going to go over them too much, just whatever is written on the paper. Yes. Anyway, I also wanted to touch on absolute value a little bit, where if we have an absolute value equation of this form, this is a very special one, which is basically a rhombus with the center at H and K and diagonals with, actually, wait, don't worry about this part, it's wrong. It's just a rhombus with diagonals of length 2a and 2b. The center, I'm not going to go into that right now. Okay. But in general, both x and y in absolute value signs, if like they're in a, actually, is this funny? Who knows? I'll have to check this. I think this might be right, actually. Anyway, in general, when you have an equation that's like, let's say x plus a plus some number times x plus another number times y plus this equals to a constant. I can't write here. Equals to a constant c, let's just say. And then basically what we know is that the graph of such an equation is going to be a parallelogram. And the way you can verify this is just using absolute values to, you can use casework on the signs within the absolute values. And then you'll just get 4 different equations. And when you graph them, you'll just get you'll just get parallel lines. So yeah, it'll just form a parallelogram. And I actually do believe the center is HK. I don't know why I was thinking of saying it's wrong, but you can just check with like 0, 0. You can graph it, and then you'll see the center is just origin. Oh, big brain time. Okay, but this is all just random stuff in coordinates. So I want to be able to use it in geometry because that's basically what the coordinate plane is. It's the mix of. It's basically the coordinate plane is basically where you can use both algebra and geometry to solve problems. And sometimes you can use this cool thing called coordinate geometry, which I'll give an example of later, in which basically you take a geometry problem and you cast it onto a coordinate plane, basically just giving certain points coordinates, and then you can use that information to find length, slopes, and other stuff you wouldn't be able to find without using it. It can be a bit tedious sometimes, so it's not recommended to do it on sort of irregular diagrams, even though it's still possible most of them. And usually you'll see them when there are a lot of right angles. So problems involving rectangles are a very commonplace for coordinate geometry problems. And yeah, this is the example I'll be going over. It's later. Anyway, and the converse is also possible. You can use geometry to solve coordinate problems, which are basically, they give you more of an algebraic problem, but then you can use the coordinate plane to turn it into geometry to solve. And basically, it's just a classical geometry problem, except for you somehow need to use coordinates to find side lengths and other things that might be useful. And with graphing, or in graphing, this isn't too big of a deal in competition math, as usually you won't really be required to be able to graph, but I think circles and lines are probably the important things to be able to draw somewhat decently in a plane. And basically, lines just write it in slope-intercept form, and I'm pretty sure you've all learned this. D is y-intercept, and then you draw it with the slope m. And circles, you just find a center, and then you can draw a radius somewhat loosely. Okay, you'll see. And yeah, well, this is just, well, just read that, I guess. And then finally, reflecting is probably the most commonly used way, or the most common way that problem writers will probably want you to change a graph, in which you basically just draw a perpendicular from the point to the line it's reflecting over, and then you extend it the same distance. And generally speaking, you'll want to draw a decently scaled diagram, and then you want to identify all the information you might need. You want to find the equations and point lines, and you want to basically treat a geometry problem with an additional task of deriving information. So anyway, I just want to have fun with coordinates today, I guess. Alright, so I'm just gonna skip right to the coordinate geometry problem I was referring to, which is this one. I'm not sure if you guys have looked this over yet, but basically, well, I'll just draw it out right here. Rectangle ABCD has AB equals 5 and BC equals 4, which means that I didn't draw this right. Let's see. AB equals 5 and BC equals 4. Point E lies on AB, so that EB is 1. So the E is here. And point G lies on BC, so that CG is 1. So let's say this is 1 and 3, like that. Point F is on CD, and DF is 2. And AG and AC intersect EF at Q and P. So EF, AG, AC, and then we know this is Q and P. Doesn't really matter which order they are in, but we'll just leave it like that. I hope you guys can sort of see what my diagram is. It's not the most clean, you could say. So we want the value of PQ over EF. There actually is a way to do this without coordinate geometry, but I think coordinates are the most straightforward way to do this kind of problem. So I just want you guys to realize that this is a rectangle, so right angles are very fun. And we know the coordinates of the points A, D, F, C, G, B, and E. Basically, we know the coordinates of all the points on the rectangle, and what that tells me is that I know I can find the equations with the lines AG, AC, and EF. And since I know the equation of the lines, I can actually find the points P and Q. And once I know the points, then I can easily find the distances that I need. So this is what I'm referring to by just when you look at a problem, you'll be able to tell if it's going to be possible with coordinate geometry, and this problem most certainly is. However, I just do want to point out that it is a lot easier to do this problem if you realize that you'd have to use distance formula to find PQ and EF. So it's much easier to actually use similar triangles, like here. If we draw the perpendicular from E down to CD, and then we also draw the right triangle with hypotenuse PQ, and the legs are parallel to the sides of BC and DC, we'll find that like PQ over EF is just equal to, I don't know this one, H. It's just going to be equal to the X, let's call this H, J, sure. And just so you can see clearly, this is going to be this right triangle right here. And if we have PQ over EF, it's going to be PJ over FH. And the point, and why I'm doing this is just because it's a lot easier to just simply find the ratio of the difference in X coordinates of P and Q and E and F than you have to use a distance formula, which is not that fun, given that these numbers aren't actually going to be that good. So basically it's just easier to find this. It's certainly possible using the other method, but this way is faster. Anyway, so usually when I face a coordinate geometry problem, I like to list out the values of all the points. So if A is going to be, first thing you do when you coordinate geometry, label the origin. Just denote one of the points as 0, 0. So basically, D is going to be 0, 0 because it's the left most or bottom leftmost, and I want all the coordinates to be positive because it's easy to work with positive numbers. This is D is 0, 0. We'll have that C is just going to be 5, 0. B is going to be 5, 4. And A is going to be 0, 4. And we know this because of the signs of rectangles. So I think that's pretty self-explanatory, at least. These are just a rectangle. It's just a rectangle. And we have that E is going to have the same y coordinate as B and an x coordinate of 4, right? So it's going to be 4, 4. And we know that G is going to have G is going to have the same x coordinate as C, which is 5, and the y coordinate is 1. And H is just going to be same x coordinate as E, and the y coordinate of 0. And F is just going to be 2, 0, like so. So we know all these points here. I'll probably need more space, but that's fine. Yeah. Okay. Cool, right? So now we want to be able to find the coordinates of P and Q, as that is basically our goal. And FH is 2, in case you didn't realize. So we just want PJ. And to find P and Q, we'll basically have to find the equations of AC, AG, EF, and then just bash out these intersection points. So yes, key skill you need to be able to do. You need to be able to find the equation of a line given 2 points. And I think you guys should be able to do this, where you find the slope first, and then after you find the slope, you find the y-intercept. So AC has the points 0, 4, and 5, 0. The slope is just going to be negative 4/5, right? Because, yeah, negative 4/5 x, and then the y-intercept is just a, which is 4. We have that AG are the points 0, 4, and 5, 1. That's going to be y equals to negative 3/5 x plus 4. And we'll just work under the challenge problem, I guess. And we have that EF, which is 4, 4, and 2, 0, has slope of 2, right? And then just minus 4, because if you plug in the 0.20, then you'll have to have a negative 4 at the end for it to work, right? So now we just find the intersection points of these two equations with EF. So first Q is going to be the intersection of EF and AC, not AC, AG. And these lines are y equals to 2x minus 4, and y equals to negative 3/5 x plus 4. And the nice thing about having them all in slope-intercept form is we just set the y's equal to each other through substitution, basically. So we'll just have 2x minus 4 equals to negative 3/5 x plus 4. So this is just going to be 13 over 5, x equals to 8, so x equals to 40 over 13, right? And then we also have that P. And notice, I just want to point out that we don't need to find Y because we only want the difference in X coordinates. So you'd only really want to find Y if you're going to check your work, which is actually advisable. But right now, we're not doing that. So it's good to find Y, but we don't have to. Just find X first. And then P is just going to be the intersection of EF and AC. Right, so this is y equals to 2x minus 4, and y equals to negative 4/5 x plus 4. And yes, 2x minus 4 equals to negative 4/5 x plus 4. 14/5 x equals to 8. X equals to 40/14, which is equal to 20/7. So now all we have to do is find this length pj and then divide by 2. And we know that pj is just going to be equal to 40/13 minus 20/7, I think. Yeah, okay. This is Q, and this is P. And this is just equal to 280/91 minus 260/91 is equal to 20/91. And we simply just divide by 2 here with FH, since that's just 4 minus 2. And then we have this divided by 2, and that's just equal to 10/91. And that is the answer. So yeah, this is basically, at first glance, this kind of problem is sort of hard to approach because we have some just lines in a rectangle without that many similar triangles. Although I do want to point out that you could actually that another solution to this problem would just be extending AG past BC to intersect with CD. Then you'd have similar triangles you could work with. And then with that, you could somehow find Q and P basically. But yeah, this way, coordinate geometry, I feel like it's really just the most straightforward, easiest to understand. And honestly, it's really not that slow of a method either. So yeah, this is actually one of my favorite kind of ways to solve a problem, just because it simplifies things. It simplifies the problem so much. So I don't think there are any other coordinate geometry problems within any of these, like of this kind of style. So yeah, I'm not really okay. Well, I got a request to do this problem again, but it's sort of a long problem, and it's often easier just to tell me which part you don't understand than to ask for it to be done over again. You just got here. Well, then I guess you could just watch the YouTube video that will probably be going up very soon. Right? Okay. But yeah, I'll just give you a brief recap. We use this cool thing called the Cartesian plane, and then we find the equations of these lines that are now on the coordinate system. And then after that, we can just find the length that we need to solve the problem. So yeah, turn geometry into coordinates sometimes. Okay, so are there any questions about this kind of method, or can we just move on? Okay, well, this was basically all of my notes that I had, although I think there are a few things I do want to give an example of. In particular, I wanted to I wanted to give a better sort of explanation of these absolute value equations. So basically, when we the most common or the most basic absolute value equation that you'll see is y equals the absolute value of x, which usually just looks something like this. And basically, the way you would solve something like this is splitting it into cases where we have y equals to x if x is greater than 0, greater than equals 0, or y is equal to negative x when x is less than 0. And basically, the same thing still applies when both x and y are in absolute values, although it is a bit sort of tedious, so it's not as fun. But let's take the equation for the rhombus we just had, x minus h over a plus y minus k over b equals to 1. You can sort of think of absolute values as a piecewise function. Although also I'll just let you know that this is 100% not a function. Vertical line test anyway. When you have absolute value around a y, it's never going to be a function. So basically, okay. So basically what you would do is you can divide this into cases where we have into cases where x is greater than h or x is less than h. I'll just put greater than equal here, or y is greater than equal to k, and y is less than k. And you'll basically have 4 different kind of ways to do this, where you'll have the pairing x greater than equal to h, y greater than equal to k, x greater than equal to h, y is less than k, and then just reverse with x is less than h. So basically, we can actually just take each of these cases. So let's say x is greater than equal to h, and y is greater than equal to h. Then we can just take away the absolute values like that. And basically, this is some manipulation I want to do. Yeah. I'll actually just not do this because I don't want to deal with fractions right now. Or basically, I just wanted to show you that this is the first case. The second case would be x is greater than equal to h. This is case 1. Case 2 would be y is less than h. Leave x minus h over a plus k minus y over b equals to 1. And then we would have x, or you have h minus x over a plus y minus k over b equals to 1. And we would also have h minus x over a plus k minus y over b equals to 1. So basically, we would have 4 equations. I just want you to know that these 2 equations and these 2 equations, they each have the same slope. I hope you can see why. But yes, they'll both have the same slope. So this is actually going to be a parallelogram. And in this case, since there are no coefficients from x and y, it's actually going to be a rhombus. So you can actually just graph this on your own if you want confirmation, at least. So anyway, I think we can just go and move on to the problems at least. First problem, something that I did not even talk about, because why not, I guess. 3D coordinates. Let points A, B, C, D, B, those things. And E, F, G, H are the midpoints of the line segments. What is area of E, F, G, H? I am getting requests to talk about the Shoelace Theorem. That's actually the cool thing in coordinates. Honestly, I don't completely remember it, so let's just say what I think it is. So basically, when you have any shape and we know the coordinates of it, we can list the coordinates out in just, I think they have to be in clockwise order or something like that. X1, Y1, X2, Y2, and so on until say Xn, Yn. Basically, if we take the products like X1, Y2, X2, Y3, and so on, you take these products, then you subtract it, and then you subtract the cross products the other way with Y1 times X2, Y2 times X3, Y3 times X4, and so on. You'll get twice the area of the shape, I believe, and the Yn just goes to 1. But this is completely not rigorous. I think I'll post something on Classroom later about the Shoelace Theorem, I guess, at your request. Anyway, there is another thing I'm going to touch upon that I did not put in the notes. So yes, thanks for reminding me at least. But anyway, back to where we were. This is not a shoelace problem. So basically, 3D coordinates is basically the same thing as 2D in most cases. So the most difficult part is just drawing. And I like to draw it like this, although it's not really like obligatory. So A is the origin, D is going to be 1, 0, 0, D is going to be 0, 2, 0, and we have D is going to be 0, 0, 3. This is 3, 1, 2, and so on like that. So you can see it's actually going to be a tetrahedron. And we have E is going to be the midpoint of BD, F, and okay, so midpoint. The midpoint of these 2 points, you just add the x, y, and z coordinates, and then you divide them all by 2. You know the coordinates of E is going to be 1/2, 0, 3/2. F, or the midpoint of AB, is going to be 1/2, 0, 0. The midpoint of AC, or G, 0, 1, 0, and H, midpoint of DC, is going to be 0, 1, 3/2. So what does this look like? So basically, if we draw this again, if E is going to be 1/2 and 3/2, this is going to be the X, this is going to be the Y, it's going to be the Z. Okay? You don't have to do it like this. Sometimes people will have the Y and Z reversed. So E, 1/2, 0, 3/2. So it's going to be like, if you think about the XZ plane, it's going to be at 1/2 here, then 3/2 on the Z plane like that. F is just going to be here. You have G is going to be somewhere here, like 0. G is going to be 0, 1, 0, and then H is going to be like here. Anyway, so basically what I want you to take away is that this is actually going to be a rectangle with the sides are F, E here, and then we have F, E, then G, then H like that. We know that FE is just going to be 3/2 because their x and y coordinates are the same. The G coordinate is 3/2. But we want to find FG, and we can find the FG basically by using the distance formula between these points. And the distance formula for 3 dimensions is actually going to be the same, except for you just add the difference of the z. You add the square of the difference of the z terms as well. So instead of this is going to be just an extra, there's going to be extra z2 minus z1 squared underneath the square root, basically. If you have questions like that, you should probably read my bio on Alphademic. Just saying. Anyway. And on tips on time pressure. Well, if you're talking about Amy, there's really no time pressure, but for AMC10, it's really just if you have the time pressure on AMC10, basically you only have like 3 minutes per problem, I think, on average. So basically, if you feel like you're spending too much time on a problem or it's too hard, just skip it. It's really not worth wasting time on. If you want to look at the next problem, I wouldn't really recommend guessing unless you're trying to make Amy and you don't have enough questions answered to actually be able to get a score that could qualify for Amy. Like if you only gone like 16 problems, you might that's actually might be okay nowadays. But basically, if you don't think you have enough problems right, then that's the only time I would guess. If you have like 18 questions answered, I would not guess. I think nowadays the Amy cutoff is like somewhere around 110. So yes. Yeah, and if you get I usually like to aim for like 120 or so as like a safe kind of score for the Amy. Like if you have 120 every year, you'll make it no problem because sometimes it fluctuates around the 110s. So yeah, those are just a few tips. I have more if you want to ask them. But let's get back to what we were doing. We have FH, or sorry, FG. We know that FG and EH are actually going to be the same length. You can actually tell just from business formulas. And yeah, so FG is going to be the square root of 1/2 squared plus 1 squared, or root 5 over 2. So the area is just going to be 3 root 5 over 4. And that's it. So basically the point of the problem is don't get intimidated by an extra coordinate, and then just draw it somewhat decently and try to envision what it looks like. And after that, it's just super easy. Next problem. The triangle with vertices 6, 5, 8, -3, and 9, 1 are reflected about the line x equals 8. To create a second triangle, what is the area of the union of the two triangles? The union of two triangles is basically going to be, basically what this refers to is, or what the union refers to at least is the total combined area. So I'm just going to say that, let's say we have two triangles. This is not the diagram at least. This looks like a very familiar picture, right? So basically the union of two triangles is going to be the total area covered by both triangles. So it's like the area of the entire star. And notice that you don't count this middle part twice. So you don't just add the area of the two triangles, basically. You do count the overlaps. You only count overlap once though. So basically, the union of two triangles is, I think it's easier to explain union, which is, anyway, the word union is sort of a concept in set theory at least. If you take a Venn diagram at least, right? The set A, set B, then we have stuff in each of these sets, right? So basically, the same concept, except the triangles at least, if you think of the sets as just triangle, which is a set of points. The intersection is this, and their union is the entire thing. Basically, everything in A, everything everything in B and everything in their intersection. And you basically, when you find the area of the union, you'd have to find the area of the intersection and the area of what's in A but not in the intersection, what's in B and what's not in the intersection. So think of it as if you take two triangles and then you just erased any of the lines that go through the shape, and you only take the outer line. That's a new shape. You find the area of that new shape. So yeah, cool stuff. Anyway, back to where we were. So we have some coordinates. The first thing you should do is graph it. Class should end at 2 o'clock every week. Although usually I drag it on later, but that's fine, I think. Anyway, triangle, the vertices 6, 5, 8, -3, 9, 1. So first thing you should realize, I have to draw this, and I have to draw it to scale to a certain extent. So you have 6, 5, like around here maybe. Then you have 8, -3, and 9, 1. So this triangle's gonna look something like that. And you want to reflect it over the line x equals to 8, which is going to be this line right here. And I talked about reflections, and you really just take, since this is a vertical line, it's really easy. 9, 1 over line x equals 8 is just going to go to 7, 1. 7, 1, and then this point, which is 6, 5, is just going to go to 10, 5. And that's simply because we're only, like, the difference in x coordinates between 6 and 8 is 2. So you have +2, and then you +2 again to get to 10. And with 9 and 8, just -1 and -1 again. And since this point on the reflection line, it stays the same. So basically, the second triangle is going to be like this. And notice how I drew each of these points on the line between 10, 5 and 8, -3, and 6, 5, and 10, -3. And this is actually the case. The diagram is actually just going to look like this. And you can tell that these points are actually on these lines simply by finding the equation of each of these lines and noticing that these are solutions as well. So we simply just want to find the area of this shape, and there are multiple ways you can do this, and they all revolve around this point right here. We want to find the coordinate of this point so that we know more about the length of the figure, and we can do that by just finding the equations of each of these lines. And so let's just take this line right here. So the slope is going to be 4/3, because 5 minus 1 over 10 minus 7, 4/3 x, and then it's actually minus, I think. Well, it's 4/3 x minus 25 over 3. And you can check that later, but it's right. And we know that the slope of this one is going to be y equals to -4/3 x, and that's going to be plus I want to say it was -33. I don't want to do mental math right now. Okay, -4/3 times 6. That's going to be -8. Okay. Anyway, actually, I just realized I didn't have to do this. You can notice that that this point must be on the line of x equals to 8 because it's like the middle. So we just plug in 8 here. So y equals to 7/3, like that. Right? Extremely legit. Okay, and now I think the easiest way to find the area of the triangle is just using base times height for each of these two halves. Right here, this is the base, and you have the height is like here, right? And 7/3 is here, it's -3. So we know that this part is just 16/3. And we also know that this height is going to be 2. So the area of one triangle is going to be 2 times 16/3 divided by 2. And we have to multiply by 2 for each triangle. So then the total area is just going to be 2 times 16/3 to the 32/3. Yes, someone has their hand raised.
So I had another idea. So couldn't you do so when you're doing your when you're finding the area of the triangle, couldn't you also find the area of a bigger triangle and subtract the smaller one? Which one would be faster?
So are you talking about like just finding this triangle, this big triangle here and stretching here?
Yeah, would that be easier? Because I think they're not similar triangles, right?
They're not similar, but they're both equally easy actually, because we know this base is just 4, and this part is 8/3. So yeah, you could just do like 4 times what was that? 4 times 8. 4 times 8 divided by 2, and then minus 4 times 8/3, and divide by 2 again. You'll still get 32/3 though.
Yeah, I thought that's the way I'm used to using finding areas of irregular things when you're on tests.
Yeah, it works. I mean, whatever suits your taste, this way works as well. So yeah, okay. You can go to the next problem now. And I don't know why I'm always late, but this is totally fine, I guess. Anyway, so we let points A, B, C, D be like that, and the quadrilateral A, B, C, D is going to be cut into equal area by a line passing through the origin. This line intersects CD, class ends at 2. The line intersects CD at a point, and what is this point basically? Alright, I'm going to be rushing a little bit. That's not fun. So we have A is 0, 0, B is 1, 2, C is 3, 3. We have D is 4, 0. Right? So basically, we know that there's going to be a line like this that's going to pass through A, or it's going to be y equals to mx at least, and it's going to divide this thing into equal areas. So to be able to figure out the problem, to figure out the problem, then what you do is you find the area of the quadrilateral ABCD. That's because that's the only thing we can really be able to figure out from here, so that we can find whatever this point is. So ABCD is a weird kind of shape, but we can actually divide it into a triangle, a trapezoid, and another triangle, like so. And we know the coordinates of everything, so we can actually find side lines. This 1 is going to be 2, this is going to be 1. This height is going to be 3, this one's going to be 2. So the area of ABC is just going to be 1 times 2 divided by 2, plus 2 plus 3 divided by 2 times 2. Yeah, and plus 3 times 1 over 2, which is going to be equal to 15 over 2, not 12. Anyway, so that means the area of triangle ADE is going to be 15 over 4. We know that AD is 4, so we know that this height right here has to be 15 over 4 over 4 times 2. That's going to be 15 over 8. And basically we know this because area formula. So now what we do is we see that this line also, line y equals mx, it also intersects with this line CD. So we can find the equation line CD, then plug in 15/8 for y, and we can find the x coordinate, and then we can find PQRS. So basically, CD is the line between 3, 3 and 4, 0. That's going to be y equals to negative 3x plus 12. And when we plug in 15/8 for y, we have 15/8 equals to negative 3x plus 12. 3x is going to be equal to 12 minus 15/8. One is actually, I don't completely remember what it was. Give me a minute. Okay, 3x equals to 12 minus 15/8, and that's going to be equal to, yes, it is going to be equal to, x is going to be equal to 27/8, where 3x equals to 81/8, x equals 27/8. So we basically have the point 27/8 and 15/8 as our solution. And if we add PQ, R, and S, you'll get that they add up to 58. So yeah, cool. We're definitely not going to be able to get through all these problems, unfortunately, unless you guys are willing to stay over. But anyway, next problem, a line that passes through the origin and both the line x equals 1 and the line y equals to 1 plus root 3 over 3x forms an equilateral triangle with the perimeter of the triangle. So again, you really want to graph the problem. Let's say x equals 1 is like that. Line y equals 1 plus root 3 over 3x. Might look something like this, except for I can't draw, so it doesn't look like that. Like that. And we know that this line going to the origin has to form an equilateral triangle. So it must look something. You're not drawing with an eraser. Like that. Okay? And that goes to the origin. And basically, since we know that the horizontal and vertical line is part of the equilateral triangle, we know that this line right here must have a slope of negative root 3 over 3. And we know this because this triangle is symmetric about this line right here. So the slopes are negatives of each other. So now, simply put, we just have to find the side length of the triangle. And we know that this line is just going to be when x equals to 1, or this y coordinate at least. It's going to be 1, negative root 3 over 3. And we also know that you might be allowed to bring graph paper, although you don't need it. And the square root of 3 over 3 is not 1/3, it is a square root of 1/3. Anyway, and this is basically taking for granted that these slopes are right for an equilateral triangle, and actually is, so you don't have to worry about that. And this point is going to be when x goes to 1 for this other equation. So this is going to be 1 plus root 3 over 3. Right? So we know that a side length of this figure is going to be the difference between the y coordinates here. So the side length is going to be 1 plus 2 root 3 over 3. So you just multiply by 3 to get the perimeter. It's just going to be 3 plus 2 root 3. So yeah, this is how you do this problem, at least. It's you draw the diagram, then you can notice cool property about the lines, and then after that, it's pretty easy to find the coordinate. And from that, you can find the distance. So yeah, this problem. For how many integers x is the point x negative x inside or on the circle of radius 10 centered at 5, 5? Now, there are actually a few ways to do this problem. I think the most tempting way to do this would just be to draw out the line y equals to negative x and the circle at 5, 5 centered with radius 10. But that way, it's sort of difficult to be precise, as you might miss the lattice point or something. So I prefer the algebraic approach to this. So we know that circle radius 10 centered at 5, 5, that's just going to be x minus 5 squared plus 1 minus 5 squared is going to be equal to 100. And I just want to, I think this is a decent time to point out that technically other points inside or on is just going to be less than or equal to that. And basically, if you learn inequalities, this is just saying that this is just referring to all the points inside the circle. As equals would just only refer to the points on, greater than would refer to the points outside the circle. So yeah, we also want the points all the points x negative x, so we can substitute negative x for y here. So when you expand, we'll just end up getting 2x squared plus 50 is less than or equal to 100. So you have x squared is less than or equal to 25. So how many solutions do we have for integers x of x squared is less than or equal to 25? And that's right. To the one person who answered, the answer is going to be 11. X can be any integer from negative 5 through positive 5. So you have 5 negatives, 5 positives, and 0. 0. You really can't forget 0. Yeah, actually, I might be able to. Okay, we'll run over a little late, but this is fine because this is an easy problem. The line 12x plus 5y equals 60 forms a triangle with the coordinate axes, or the sum of the lengths of the altitudes of this triangle. So before I mentioned that you wanted to convert it into slope-intercept form, but in this case, it's actually easier to graph it as it is because we can just use the x and y intercepts. As we know, the point 5, 0 and 0, 12 are on this graph. And it's pretty easy to see if we let x and y equal 0, this is just obviously true. So we know that this graph looks something like this. And this triangle is going to be right here, as you can see. So we want to sum the length of the altitudes of this triangle. And we know that the altitudes are just the perpendiculars from the point to a side length. And so we know two of them already are 5 and 12. But how are we going to find the perpendicular here? That's the question mark, not a 2. So basically, this is a Pythagorean triple. So this is 13, right? Easily verified. And basically what we do is we use this property of altitudes is that the altitude times the base is just going to equal to twice of the area, right? And so what is the area of this triangle? The area of the triangle is going to be 30 because 5 times 12 divided by 2. So we know the altitude is going to be 30 divided by 13 times 2 equals 60 over 13. And then we just add all these altitudes to get our answer. And voila, you're done. Second to last one. Although challenge problem I'll just not really do much about. Okay, what is the area of the region enclosed by the graph of this equation right here? And this thing is pretty interesting because this thing's pretty interesting, at least because you have x squared and y squared, we have to have two absolute values. And I mentioned this before, this is actually just going to be a weird sort of circle thingy. It's not entirely a circle. And I can show you why. So basically, we have x squared minus absolute value of x plus y squared minus absolute value of y is equal to 0. And you can do casework on x and y. X greater than equals 0 or less than equals 0. Less than x or y is greater than equals 0, y is less than. So basically, first thing you should realize is that this equation is symmetric. So if we take this x greater than equals 0 case, y is greater than equals 0 case, and graph it, then we can just simply do the same thing for each of the other quadrants. I'll demonstrate. So basically, when they're both greater than equals 0, this can be the first quadrant. If x squared minus x plus y squared minus y equals to 0, so x squared, you have to complete the square at least, x minus 1/2 squared plus y minus 1/2 squared is equal to 1/2. And this is basically, I just added 1/4 plus 1/4 here, plus 1/4 here, and plus 2/4, like that. And you can check this as well. And what is this? This is a circle centered at 1/2, 1/2, with radius of √2/2. So when we graph that, there's literally a grid right here, but I'm not using it because it's too big. And I didn't draw this very well. 1/2, 1/2, let's just say it's here. And the radius is √2/2. That means that if we draw the hypotenuse here of a 45, 45, 90 triangle like that, yeah, whatever. You'll have that this length is √2/2, √2/2, and then these are actually just going to be sides of length 1. And this is also the reason. And why does, basically we would have that it looks something like this, where we have a semicircle and then a right triangle. And why is it not just a complete circle like this? It's because, well, technically it does work, but it's because we have the restraints x greater than equals 0 and y is greater than equals 0. So we don't consider any points that are not in the first quadrant. So with that in mind, we can actually just draw the complete graph using this cool thing called inference, where if we just draw the same thing for each of the other quadrants, we'll get the graph look something like this. And this is pretty easy area to find. We know that this length is just going to be the square root of 2. The area of the square is 2. And we also have 4 semicircles, each with the radius √2/2. So 4 times 1/2 times √2/2 squared pi. That's just going to equal to pi. So our area is just 2 plus pi. So yeah, that's this problem. We are slightly over time, so might as well drag it another like 2 minutes. Anyway, finally, last problem, challenge problem. We have the points A is 6, 13, and B is 12, 11. Let's say it's a 6, 13, and 12, 11, like so. We base it, and we have that tangent lines to a circle that passes through A and B, intersects at a point x-axis. What is the area of the circle? So it's like something like this, and then have a circle like that. So at first this looks really, really weird. You don't have much information about it. You don't have any information really about the circle. Well, you do, but not really. You don't really know what point intersects the x-axis. Therefore, it is on the x-axis, and that's about it. So I won't really be solving this problem, but I just want to give you guys a starting hint, and it's just, you know, you can use the two tangent theorem, where if you have a circle and then you have the tangents from a point to the circle, these two lines are going to be the same length. So we know a point x0 is equidistant from 613, and 1211. So my proposition is that, or my plan for you guys at least, is find x using the fact that these lengths are the same with a distance formula. After you find x, then try to figure out what this diagram sort of looks like and how you can find the equation of a line that passes through the center of the circle. So yes, somewhat cryptic, but not really. Anyway, so yeah, that's gonna be it for this class. Yeah, you guys can leave if you want. You can stay if you want for some reason. But yes, bye-bye.